Everyone. Thanks for taking the time to be here and offer your support. Thank you to the panel members for convening, especially Iman, who flew here from Canberra. Thank you for being here. And thank you to my supervisory panel, so Professor Michael Milford, Professor Nico Sunderhoff, and Dr. Tobias Fischer, for putting up with me for way longer than anybody should reasonably have to. So anyways, I'll be talking about the work that I'll be including in my thesis today, work that I've done over my PhD, and the topic of my thesis will be bridging the divide between visual place recognition and SLAM. And so I guess if I'm candid about it, you finish your PhD with a few bodies of work, and this seemed to be the unifying theme that reasonably ties everything together. So the structure of this talk will be like most final seminar talks. We'll provide a bit of introduction and high-level motivation and context. We'll provide a bit more of a detailed background on simultaneous localization and mapping, or SLAM, as well as visual place recognition, as well as what bridging the gap actually entails in terms of the work that I've completed. We'll actually go and do a bit more of a deep dive in the actual projects themselves, of which there are 3, and then we'll conclude with a little bit of future work. So the high-level motivation when we think of simultaneous localization and mapping and place recognition is around navigation. So specifically for mobile robots, and we deal with the mapping and localization subproblems. So we want robots to be able to position themselves in the world and to be able to move through the world as well, to actually navigate. And the problem that I am particularly interested in is dealing with what we call long-term autonomy in large-scale environments. So we want the robots to position themselves reasonably well in very large environments, and we want to do so in a way that's robust to changes in the environment. So potentially somewhere where this stuff could be used is around GPS-denied positioning systems, and it could be quite relevant to autonomous vehicles and drones, especially where GPS is not available. So with SLAM and visual place recognition, there's a lot of history between SLAM and place recognition. If you know anything about SLAM, you know that place recognition is historically used a lot for loop closure detection in SLAM. It's very important as a subcomponent within an actual SLAM system. But in this talk, we're going to look at it from a slightly different angle. We're going to look at the distinction between metric maps, so those generated by SLAM, compared to topological maps. So with metric maps, so the figure on the left at the bottom is generated by CSIRO's Wildcat SLAM system. So this was used in the DARPA Grand Challenge recently, and this is one of the state-of-the-art methods to be able to do that. And what we mean by globally consistent metric maps is we want to provide a very accurate reconstruction of the geometry of the environment. That's one of the goals of many SLAM systems, is to actually deal with the geometry. And this is useful for a number of reasons. For example, with surveying, maybe the end goal is to understand the dimensions of the space that you're actually operating in. Whereas from a navigation perspective, arguably maybe topological maps and navigation systems could be a useful alternative. So with topological maps, we deal with storing much higher level information. So we don't store explicit geometry, we don't care about centimeter precise reconstructions of the environment. We simply care that the environment, or the topology of the environment. So we have an environment, maybe it's comprised of a set of places. So this is represented as a graph. Each place might be connected to other places based on some notion of proximity or traversability. And we store high-level appearance information rather than metric and geometric information. So we'll dive into the first topic. So we're going to talk a little bit about simultaneous localization, mapping, and place recognition. So a little bit about SLAM. So it's actually a very descriptive name, right? So the robot is simultaneously, so we have a moving robot. So in this case, this is OrbSLAM from the University of Zaragoza. I think many people have been exposed to this, of course. So we have an autonomous car. This is the robot. It's mounted with specialized machine vision cameras. So this is in the KITTI dataset, and a LiDAR. And the the robot's moving through the environment. It's building new points. So this is mapping. You can see the red points there. So there's a bit of mapping going on. And as it's building up its representation of the environment, it's also positioning itself with respect to this representation that it's actually building. And you can use a variety of sensors. So we mainly look at cameras in this work, but you can of course use LiDAR, radar, Wi-Fi, sonar. There's lots of interesting things, GPS encoders, of course. But it's all very descriptive, what simultaneous localization and mapping is. You can see like this is a reconstruction of it. I think this is Carlsberg KITTI dataset. So I would argue that simultaneous localization mapping, so SLAM is really fundamentally an estimation problem. And so really what we want to do is we want to recover the trajectory of the robot and the environment geometry using raw sensor data. And there's a big focus, I think, in a lot of SLAM research on reducing the estimation error, this idea of global consistency. When we build a map, we want to reduce the error of estimation through our raw sensor data, and you propose algorithms that do a better job on benchmark data sets. And without delving into it in too much detail, this is the stuff, this is the stuff that I like. How you actually do this, well, I think the two dominant paradigms would be probabilistic filtering, where you track probability distributions over robot state over time and integrate sensor measurements incrementally. And we also have nonlinear optimization. So you've probably heard of pose graph optimization. This is trying to find the most likely configuration of the robot in the environment jointly using the sensor data. And these are two very different methods, and we're going to tackle both in our work in the context of topological mapping. So metric maps in SLAM, I think, are really great. I certainly played with a bit of structure and motion during my PhD. And so when we look at a particular case study, like a particular instantiation of mapping and localization, and we think of visual SLAM, a lot of visual SLAM algorithms, what they provide to you is they provide a 3D reconstruction of the environment from a moving camera or multiple images. So what you get is you get this big point cloud. So you see on the right, you get this really large sort of point cloud. You can have hundreds of thousands of points per kilometer traveled, same autonomous vehicle. So you have lots and lots of points, and each 3D point represents a 3D landmark in the world, and each point also has some sort of appearance information stored. So you've probably heard of SURF and SIF descriptors and stuff, and then those descriptors would be associated with each point. To do the actual mapping, there's a nonlinear optimization subroutine. So you might have heard of bundle adjustment, so global bundle adjustment. And this nonlinear optimization is actually used to construct these maps and to triangulate the 3D points from 2D views. Localization is also a particular thing. So in this case, we do geometric pose estimation. So we're trying to estimate the rotation and the translation of the camera with respect to the actual map that you build. So there's geometric optimization problems as well as a robust estimation pipeline running in the background as well. So this can be very computationally demanding. But if you do have the 3D geometry of the environment, so in principle, in practice, obviously things are not so easy, but using these 3D points, you can get an idea of what's traversable, what's not, what is occupied space, what's not, and you can interface this with motion planning algorithms because of this reconstruction of geometry. So we're going to contrast this with topological maps in a moment to motivate why they might be useful. But really, there's a bit of an existential question, and I think people have thought about this for a while, and this certainly haunted me during my PhD, is the question that, do we really need these high accuracy metric maps to actually perform the task of robot navigation? So of course, surveying is a different task, but in terms of navigating the robot through the world, being able to position and even do motion planning, do we really need these globally consistent metric reconstructions? This is something that's interesting to me. And so, I'm not a neuroscientist. I've read a little bit on this, but people, rats, bees, like insects, certain types of animals, which you can run experiments on, a lot of them have shown not to do these 3D reconstruction methods, and maybe this isn't surprising. So maybe bees do shoot lasers out of their eyes, and they do this optimization in their head, and then they have an idea of where the free space is, but it seems a little bit implausible to me. And I think that motivates this idea of topological mapping. So topological maps and positioning yourself in a topological way, and the way we implement this is using visual place recognition. So this is a figure taken from a recent paper of ours. The idea of topological maps is the map is actually represented as a graph. So if we just look at the blue line, we have a map. It's a set of places. So these are nodes. These are the points. And we have edges connecting places. And this is due to proximity because we have a vehicle moving through the environment. This is how the map is built. So we represent everything as a very high-level representation as a graph. And at each node, each place, we store some notion of appearance. So what do things look like at this place? There are many different ways to skin this cat, and we'll be dealing with one particular way in our work. And if we include motion information in the edges between the places, we have what we call a topometric representation. So visual place recognition, or VPR, it's typically an image processing method. To do this appearance encoding that we need for topological maps and localization systems. So the map is comprised of a set of reference images. So we have this database of images, images where the robot's been, and captured views at those places that the robot has actually been. And given a query image, so we want to position our robot now. So this is what the robot's seeing now. Let's find the most likely location that it's in, right? So this becomes actually an image retrieval exercise. So we want to retrieve a relevant reference image that's captured at the same location given a query. And so, of course, deep networks are everywhere, including place recognition. It makes a lot of sense. Lots of new data sets and network architectures coming out to address this place recognition problem, and benchmarks as well. And so the way that it works is you have a query image. So we look at the bottom. Let's say we have a single query image. We do a bit of image pre-processing. We feed it through a deep network. So this is what the deep network methods do. You get some feature maps, intermediate feature representations of the environment. You aggregate this into a reasonably low dimensional vector called a descriptor. All the reference images have also been converted into descriptors. And really, localization becomes retrieval. It becomes nearest neighbor search. And there's like approximate nearest neighbors. There's lots of ways to do retrieval of vectors in Euclidean space in ways that are fast and can scale up to very large data sets. So going back to the visual SLAM example, so we talked about things like memory, how do we build these maps, how do we do localization? It's fundamentally quite different with topological maps. So now, in terms of memory, like what do we need to store in terms of these maps? We don't have big point clouds with lots of appearance information in there. We simply have a sparse set of places, and each one has a relatively low dimensional embedding associated with it that just encodes the appearance. In terms of mapping, we're adding new nodes into the graph. So topological map is a graph. So we're adding new nodes and we're connecting existing nodes. And connecting nodes is actually very similar to the localization problem. So mapping and localization are very similar. And again, localization just becomes a retrieval nearest neighbor search exercise. So there's lots of, well, at least at the moment, at this point in time, there's some possible relative scalability benefits of using topological systems for mapping and localization. And motion planning is pretty sparse, to be honest. So Milford et al. In 2010, so this is persistent navigation and mapping using a biologically inspired SLAM system, did navigation, so motion planning and everything within an office environment for 2 weeks. And this seems to work reasonably well. So it's been demonstrated to work in certain environments in the real world. This is more recent work from University of Washington by Xiangyang Meng and Dieter Fox's lab. If you can see the video here. And what it's doing is you have a robot and you're simply using a monocular camera. So there's no information about geometry and a purely topological map to actually do motion planning. So this is the robot actually operating in the real world. So especially with new technology, with deep networks, which is proliferated, which is everywhere now since 2010, there's promise that we can actually develop controllers for these systems as well. So we might lose the geometry of metric maps, but it is still possible that we'll be able to deploy these systems on actual robots, eventually. So that sort of motivates it. I'm very interested in how do we bring topological maps onto robots in the real world. And there's still, work to do in that space, lots of work to do in that space. And we'll talk a little bit about that later. So now we're going to talk about, so we talked a little bit about simultaneous localization mapping and these metric maps and these topological maps. And we're going to talk about how my research combined these techniques. I like all the math and the techniques, and this is how it came to be in the end. So one way is certainly methodology. So in SLAM, we touched on probabilistic filtering and nonlinear optimization. So we wanted to take these techniques and combine them with topological methods, which are encoded using place recognition. So we didn't want to compromise the scalability. We wanted things to still run very, very quickly using the retrieval formulation, but we really wanted to improve localization performance from a place recognition perspective. And also there's the question of capability as well. So place recognition systems, at least, typically you come up with a new image processing method, and we've done that in this group, which improves retrieval performance. So given a query image, let's make sure we bring up the right match in the database. But problems like uncertainty quantification, what about mapping? How do we build out the actual database? How do we incorporate robot trajectories to actually build the map? How do we do that? There's not much work on that, as well as addressing more SLAM-like problems like kidnap robot or global localization. You run the robot until it has some certainty on where it is, and then you can propose a position. So ultimately, it'd be great to move towards this idea of a topological SLAM system in the future. So I guess with the background out of the way, I'll start talking about the projects themselves. So we'll talk about, it'll be a sequence of 3 papers. And so the first one is by myself, Nico Sunderhoff and Michael Milford. And the paper title is Probabilistic Visual Place Recognition for Hierarchical Localization. So that was published in Robotics and Automation Letters in 2010. And what we did in this work is we wanted to take retrieval, so state-of-the-art based place recognition, and two of the methods have neural networks that we evaluated on, and we wanted to combine that in a reasonable way with probabilistic filtering algorithms. So we developed a discrete hidden Markov model, which we call a topological filter, as well as a continuous state particle filter. And what this provided us, what this afforded us, is by combining retrieval with filtering, we got quite reasonable uncertainty quantification. And we can use this uncertainty quantification to actually make decisions in terms of whether or not we should accept or reject our current best estimate as to our position. And also we evaluated on the online global localization task that you see in like metric maps. So you run the robot until it's fairly certain as to where it is. It has no prior belief as to where it is. And we evaluated this in fairly challenging and large environments. So with probabilistic filtering, this is pretty classic. So the picture on the right is from probabilistic robotics. Got to read that book, right? And these filtering methods, what they do is they track some underlying posterior belief. So if you look at the top with the yellow, we have a robot, it's initialized, has no idea where it is, like uniform. So it could be anywhere in the corridor. These are the states. It has no idea where it is. And it can take measurements. So if it sees a door, oh, okay, we look at the yellow, it's probably more likely to be near a door than not. And as you move, it updates the belief as well. So we have a motion model, which is when the robot moves, and we also have a measurement model when the robot makes observations. Okay. And we adapted this to place recognition. So if you see, again, what I mentioned was we have these image processing methods. So you take an image, you embed it into a descriptor, and then you compare the descriptor similarities. And this is what we're doing here for 3 different image processing methods. And for each of these 3 methods, what you sort of see here is you see a bit of a peak. The robot is actually here, like it's actually where the peak is. So we designed a measurement model. We transformed the similarities to maintain peaks. So where there are peaks, and it turns out peaks actually correlate to performance. So where there are peaks, it's actually more likely to yield a correct match. Our method actually accentuates the peaks. But when the peaks are not there, nothing is accentuated. And sort of the key insight of this work, maybe somewhat retrospectively, is that when you have less perceptual aliasing, so when there's less environmental changes, less appearance change between your query at deployment and mapping during reference, it naturally actually has a lot less certainty in the measurements. Right? And this is what I observed experimentally on this particular data set. And so during rain, you see these distinct peaks, whereas at night, using the same measurement model, we have a lot of uncertainty in the measurements. And so uncertainty in the measurements actually translates to uncertainty in the belief. So the hypothesis is if we utilize the uncertainty in the belief to accept positioning estimates, we can actually reduce the failure rates. And so we evaluate on this global localization task, this online task. So we actually process images one by one. We update the belief incrementally until the belief is fairly confident as to where it is. There's concentration in the posterior belief. And then we wait until a certain degree of confidence before we actually accept the match. And the actual latency, so how long it takes for our model to converge, really depends on the degree of aliasing. So it's very dynamic. So at nighttime, what actually happens is if image retrieval is fairly inconsistent, your model won't converge, but eventually it will. And when it does, it tends to find the right solution more often than not. So we compared in this case against other methods of place recognition, which does sequence matching or graph search. And we believe that the reason why our methods work substantially better is the fact that it embraces this uncertainty. So we evaluated this on the robot car data set. So we have a reference traverse on the left. You see the conditions are fairly overcast, nice English day. And on the right 2 columns, this is the sort of appearance change we're dealing with. So rain, there's not too much difference, but with dusk and night, it's pretty bad. I don't really know what's going on myself when I look at these images. So across challenging conditions, we see the most performance gains, and we can substantially reduce the incidence of failure rates. So if we look at this particular cell here that my mouse is over, so when we use the NetVLAD image processing pipeline and we use a discrete filter, 92% of the time it converges, so belief converges, and 92% of the time it gets within 5 meters of where it should be based on ground truth, and it fails only 1% of the time, and usually it's just outside of 5 meters. And again, what I mentioned, this thing about localization latency is that where things are less ambiguous as to where you are, things converge a lot faster. So we'll move on to the second project now. So we extended the work in our first project. So this was work with myself, Tobias Fischer, Nico Sunderhoff, and Michael Milford. So this paper is called Probabilistic Appearance Invariant Topometric Localization with New Place Awareness, also in Robotics and Automation letters. So we wanted to extend the capability of our method. So we wanted to move more into mapping. So a lot of place recognition papers don't account for the fact that your robot might not actually have a corresponding place in the actual database. So with retrieval, you're trying to find the correct match. But in this case, maybe what you should be doing is you should be saying, I'm nowhere in particular. I'm not actually within the previously mapped area. So you see the blue will be the map in this case. I use robot car a lot. And so blue is the reference traverse, and red is the actual query. So we see some pretty significant root deviations. So there's some degrees of overlap, but there are also some differences as well. And we want to be able to handle this. And rather than looking at the online localization context, where we want to figure out where we are as soon as possible, we do the offline mapping problem, where we can process the entire sequence in parallel together. So this is more moving towards the mapping task. If we can find a way to combine two traverses, we have the basic of a topological map. Now, the previous filters, this is pretty straightforward, but has a very strong prior. So what happens is, let's say we have 5 places in the environment and we're at place 0. What we're saying is we can only move within a neighborhood. There's no possibility that we're actually leaving. Whereas what we do is we add a new state to our hidden Markov model, this off-map state, the shortcut state, so the robot can actually leave and then come back again at any time. And these transitions are actually informed by odometry. So if blue is the reference and red is the query, and we're dealing with a root deviation, the belief starts off very confident that we're in this spot, and then over time it moves away from the map, and a lot of the belief mass shifts to the off-map state. I don't really know why there's no peak there. Maybe I put in the wrong image. And so again, when we're dealing with the offline mapping problem, what we can actually do, rather than global localization, we can actually do backward smoothing. And so what happens is if we're processing the whole sequence offline, so with forward filtering at the start, we have our first measurement. The robot has fairly low certainty as to its position, and over time it increases. The level of degree of certainty increases. Backward smoothing actually takes future measurements and uses that to refine the belief at time 0. And so we can use this to our advantage for this offline task. And again, we use filtering and we use uncertainty to make actual decisions in terms of data association. And so we evaluate on RoboCar again, but we use different traverses. So here we use the purple and the red, which have significant root deviations to the actual blue. So we want the robot to infer that it's not within the map when it's not, and we want it to infer that it is within the map when it is. And unsurprisingly, if you explicitly model root deviations, things work better than when you don't. So we see some very strong performance gains. And the figure on the right is a little bit horrible, but I'm going to try and explain this. So with blue, this is the reference. So it comes down, it takes a right turn, and then it takes this loop clockwise, and then it comes back the way it went. Whereas in the query, this case, it actually deviates immediately from the root, and then it takes the loop this way, so it re-intersects with the map, and then it actually makes another root deviation here. And our method in green can actually handle these very gracefully and recover very quickly, whereas the other filters cannot. So a limitation, and this is something I would like to work to, is moving away from just localizing a single traverse, so combining a single query and reference traverse, and we want to move towards multi-session mapping. So we might have all 5 of these, and we want to be able to combine these into a general topological map, a graph, in a meaningful way. So finally, I'm going to talk about the last project, and this will be a bit of a deviation. So we'll see how we go. And so this is a joint paper done by me, so Mingda, Saurav Garg, Michael Milford, and Stephen Gould at the ANU. So this was a cross-institution collaboration. And the paper is called Deep Declarative Dynamic Time Warping for End-to-End Learning of Alignment Paths. So this is currently under review at ICLR 2023. And we finished the rebuttal on Saturday. So it's very, very recent stuff. And so we want to really move away from filtering. So rather than looking at probabilistic filtering, we're now looking at nonlinear optimization. So this project was actually motivated thinking, rather than doing filtering, we can do something like the Viterbi, some sort of nonlinear optimization formulation to do this localization problem. So we have a query image sequence. You see the orange points, and then you see the blue points, the reference sequence. And we want to use nonlinear optimization to actually do the matching. So the output, so the sequence of matches, actually comes as the solution to a nonlinear optimization problem. So this is kind of like analogous to pose graph optimization in SLAM. And what we really want to do is we want to improve the quality of the alignments. We want to reduce the estimation error or the positioning error produced by these alignments. And this optimization is actually naturally based on the dynamic time warping problem, which I'll explain in this context. So when we look at query and reference sequences, we have two sequences, and we have this alignment. For each query, we want to match it somewhere inside the reference sequence. So this is what we call the temporal alignment. And these query sequences and reference sequences can fundamentally be thought of as a time series. We have a sequence of images, which become embeddings, low-dimensional vectors, and they have timestamps associated with them as well, and this is naturally a time series. And so really what we can formulate this sequence-based localization using place recognition as is this temporal alignment task. So we can achieve this using dynamic time warping. So this is a query, we match it against a reference, and what actually comes out is a temporal alignment. A little nuanced detail is usually the reference sequences are much longer than the query sequences, so this ends up being a subsequence alignment. So we have a shorter query sequence registered against a longer reference sequence. And what dynamic time warping gives us is the minimum cost temporal alignment between two time series, more generally. So this is DTW has been in signals processing and time series analysis for a long, long time now. And so what DTW wants to give, so what DTW gives us is from a place recognition perspective, we want to find a sequence of matches between query to reference, which minimizes the total visual dissimilarity. And these matches are subject to constraints, so we're not just doing retrieval. There are temporal constraints and also regularization on the matching as well. And the match sequence is what we call an alignment path. And so in terms of DTW, what are we actually doing? We actually take a continuous time variant of DTW called the generalized dynamic time warping. So it's called general optimization formulation for dynamic time warping called GDTW. So this is a paper by DeRiso and Boyd from 2019. So what GDTW allows, it allows interpolation of matches. So the original DTW algorithm, for those who have heard of this, is let's say we have two univariate time series. So we have X and we have Y. And what DTW gives us is it gives us a sequence of matches between observations. So here what we can see, the black line is one observation in Y matches to an observation in X. So we have this discrete data association, and this gives us an alignment path in the pairwise cost matrix. GDTW actually allows interpolation. So rather than matching an observation to an observation, you can actually match, say, a query image in between two reference images. So this interpolation actually affords us greater accuracy when doing this temporal alignment task, which is great. So we effectively move from this warping path, which is discrete, to a continuous warping path, which is piecewise linear. All right, so we actually changed the optimization problem. And part of the reason why we use this new formulation for DTW is we can actually embed this into deep networks using bi-level optimization. So because we have a continuous, and this is important, which I'll get to in a moment, because this GDTW is differentiable, and I'll explain how this is, we can actually differentiate through the predicted alignment. So in terms of a place recognition context, what we really want to minimize is we're aligning a query sequence to a reference sequence, and that might induce some sort of GPS error. What we'd like to do is we want to actually train our deep networks that do this image processing to further reduce the GPS error. And we're doing the sequence alignment task. So usually these deep networks are trained to maximize single image retrieval using contrastive learning. But here we want to retrain these neural networks to better handle the sequence alignment task. So what we really want to do is we want to say, hey, let's minimize the GPS error across the sequence. And we want to be able to backpropagate gradients all the way to the underlying feature extractor. So you see here, this is a system diagram, which I have hacked together. We have query images and reference images. That gets passed through image processing to get these image embeddings, these descriptors. DTW generates, or GDTW and DEC-DTW generates this alignment path. And this alignment path actually has an associated GPS error. And so we want to backpropagate things all the way back. We need this alignment step to be differentiable more fundamentally. And how do we get this differentiability? We use this thing called deep declarative networks, which I'll be talking about tomorrow if you'd like to come along. And so bi-level, it's all about bi-level optimization. So the original deep declarative networks paper by Gould et al. Has all the details in there in the math, and we'll talk about this a little bit. And so this is bi-level because we have this outer problem. So we want to minimize the GPS error with respect to the features using SGD, using gradient descent, right? But to actually compute the alignment error, we need to solve another optimization problem in between. So there's two layers of optimization. There's an inner optimization problem given by DTW, and then there's an outer optimization problem given by the GPS error, and that's what we want to solve. The way we can actually achieve this is because, I'll touch on this very briefly, is it turns out this continuous time DTW, this GDTW, we can actually formulate this as a continuous inequality constrained nonlinear program, or NLP. So what this means is phi is the warp, so we want to find a temporal alignment, this warp, which minimizes this objective function subject to constraints. So there are constraints on the actual warp, like monotonicity. Your time warp can't go backwards in time, for instance, would be a common one. And assuming we had this NLP representation of DTW, once we solve the NLP, we're actually at a solution. So the local minima of the Lagrangian, so we're satisfying first order conditions of optimality for this DTW optimization problem. We can actually compute the gradients using a formula here. So if we want to differentiate the warp with respect to the inputs of the time series, we can actually compute this analytically using this expression, and we can do a bit of fun sparse linear algebra, so lots of linear algebra tricks, and automatic differentiation to actually achieve this very quickly. Yes, that was fun. Okay, so what did we do in terms of place recognition? So we actually, retrained NetVLAD and these feature extractors to do the sequence alignment task. So we wanted the sequence alignment task to be better. So we have all these dots. These are the query images here, right? And the blue are the reference. And so the baseline, which is in magenta. Sorry, I'm very bad with colors, but the pinkish one. These are the pre-trained NetVLAD, trained for single image retrieval. You're seeing here, it's projecting onto the reference sequence in the wrong spot. So there's a little bit of alignment error here. But then after we actually do the fine tuning and we train it, we're getting the projection to be much more reasonable. And this actually holds across an entire unseen test data set. So the top are the query images and the bottom are the reference images. So we have some degree of appearance change between these two. So yeah, we just took the single image data sets used to train NetVLAD and we bootstrapped them into sequences algorithmically to actually train this neural net. So it was actually quite easy to do so. And compared to the relevant baseline, so this is before training, especially when it comes to error thresholds at 2, 3, 5%, we can actually show big improvements. So here, this number here is saying that 21.5% of test sequences had a maximum error of 2 meters across the whole sequence. So this is what we're evaluating on. So we can see very significant gains in performance. And because DTW is so general, the other experiment we did is actually around music information theory, like music information retrieval. Yeah. And so DTW is of general interest to speech, music, and video learning. And so we applied DEC-DTW, this sort of training, to what we call what other people call the audio to score alignment task. So the goal is, in this case, we have someone playing the piano. So we have an audio recording of someone playing the piano, and we want to align it to the underlying sheet music. That's the goal, right? And we found a data set where we can actually find ground truth alignments. We can actually derive that for piano recordings. And after training, we can also see big gains compared to the baseline as well. So there's a bit of generality to our approach. So we evaluated on these 2 real-world experiments for DEC-DTW. What I think is really cool for this is, I guess the idea was driven by PlaceRec, but I think this is a more general contribution to time series learning and signals processing in general. So this is why we submitted to ICLR. So now that's the end of that. So I'll end with a bit of future work. So in terms of topological mapping and navigation, which I quite like, what we really want to do again is we want to extend our second project doing this topological mapping to a full system. So we want to actually deal with a multi-session mapping problem. So on the right, we have the NCLT data set. So this is University of Michigan, captured by this robot Segway here. And you have so many different traverses with all these different route deviations. This data set's on a university campus as well. So you have much more wide open spaces. It's much more challenging for evaluation of these systems. And we really want to extend our work to be able to handle many, many sequences. So we want to take that and build this into a general topological multi-session mapping system. And we want to test it on more data sets to iron out the kinks so it can be more generally used and deployed. And finally, I'm very interested in topological motion planning. So I wrote a little bit about that in my thesis. So we saw the example from Dieter Fox's lab from Xiangyang Meng University of Washington, and a lot of their experiments are indoors on real robots, which is great, but still indoors. It'd be interesting to abstract their approach and their controller design to actually work on more open spaces and outdoor environments, and to deal with actual appearance change in between mapping and deployment. So I think PlaceRec can be quite useful for that. And I guess just a conclusion, I'm certainly within time, that's good. Topological systems, I think, are an interesting alternative to metric systems for the task of robot navigation. I think combining methods from SLAM, like filtering and place recognition, gives you meaningful improvements, at least in terms of uncertainty quantification and performance. We can tackle new tasks using image retrieval systems, such as global localization, kidnap robot, and mapping. And finally, dealing with nonlinear optimization and place recognition. This showed great performance improvements in terms of increasing the accuracy of the actual system, similar to what postgraph optimization does for SLAM. And finally, I guess this is another point, is that DECDTW, our recent work, is actually a more general contribution to time series inspired by place recognition and topological navigation. Anyways, that's it. Thank you for listening, and plenty of time for questions, I think.
Questions on the panel? I think you almost answered my question. When you talked about smoothing,
yeah.
When you started talking about nonlinear optimization thing, you suggested it's a smoothing problem. What did you mean by that? Because
oh,
you have to be...
right. Yeah, exactly. Yeah. So when I say smoothing, this is because I've read a lot of robotics papers, and there's a lot of papers that actually refer to smoothing as maximum a posteriori estimation. Even though smoothing, with filtering, you can do backward smoothing, right? To go back in time using these Bayesian methods. So what I mean by smoothing is, we use nonlinear optimization to find the most likely sequence of matches. So before, with the filtering methods, we were iteratively updating a distribution of matches. And here, what we're doing is, we're using nonlinear optimization to find the most likely sequence. And this is what I mean by smoothing. Is it this?
I wasn't there, because you use smoothing in those two
senses.
Yeah,
I realize that is, thanks.
And then the other thing is, when you talk about topological map and symmetric map, one thing that is not clear to me, when you're abstracting a topology, any node in a connected space in the topology is equivalent. How can you choose to put 5 in the same connected space? Go to the beginning of when you had to comparing the Zyro. For example, on the right, if I want to be very annoying, I'd say all this connected space, topologically they are really the same space. Why aren't they the same node?
Sure, right.
How can I pick all these bits of it willy-nilly putting nodes on the ground?
Right. So that is a good question, and I think ultimately it's what you really want to do with that. So you're talking about, let's say, the corner or something. You have a connected, maybe you have a clique or something. You can turn this into a single place or a node, but it depends. Maybe you want your robot to actually be able to go to this corner, for instance. So maybe you do actually want to separate this point from this point. So I don't really have a satisfying answer, because we never really thought about how do we sparsify in a meaningful way, because it really depends on whether or not you want to do motion planning with it and stuff afterwards. But I think, that's certainly something that would be interesting in future work, and I think there is stuff in the literature around this.
How many questions?
Couple more.
You stop me. The other thing is that when you talk about the accuracy of VTR, you're imbuing the topological space with a metric.
Yes.
But then you say it's not a metric SLAM.
Yes.
It's a bit confusing. Can you?
Yes. So there's a bit of context. Like for this particular, so for the first work, there's hierarchical localization in the name, and so hierarchical localization is if you have a topological map which indexes a metric map. So there's an initial retrieval stage where you need to get close enough for the actual geometric pose estimation to work. So depending on the actual application, if you're doing direct image alignment, then you have a much lower basin of convergence. It's very important that metrically your topological system will get reasonably close enough. So I think it depends on context. And also with motion planning as well, and this is high level sort of future work. So suppose you have a trajectory, which was what the robot did as it was mapping, and you want to be able to position yourself relative to that close enough such that your controller will actually be able to track the trajectory. So maybe there's some sense of, if you localize topologically and it corresponds to something attric-metrically, this might be useful for downstream applications like, hierarchical localization or motion planning, is the point. Yeah, so we do evaluate using metric. But I suppose maybe this could also be something interesting as an alternative to GPS, because we can still get within 5 to 10 meters without GPS. We just need images and image retrieval. So it depends on what you want to do with it afterwards. And admittedly, I have not done a satisfying thing because I haven't really done any downstream applications from there.
I will ask one last little question.
Sure, yeah. I've got nothing else to.
You have this observation that, for example, at night, the accuracy of your place recognition system drops. Have you looked at that? That suggests to me it's a measure of the frequency response of the picture that you're looking at.
Right, yeah.
Because you lose edges.
Yeah.
The moment you lose edges, your Fourier transform, which is a 2D signal, really, when
yes.
the value drops off. Have you looked at the frequency representation of these images?
No, I am aware that there is work around that, but I think the last time I read a paper on that was more than a year ago. I think there was a.
Because I think that can explain a lot of these. Maybe this is wrong. There's a good chance that this is wrong, but I think that might explain why you lose edges, you lose all the high frequency harmonics. You've done.
Yes, yeah, you lose edges. Motion blur everywhere, which further wrecks the edges. Perhaps imbuing this structure into the actual deep networks for perception could be actually quite interesting. I think that's a general theme of a lot of my work from now as well, is how do we imbue this information into deep networks in a meaningful way. Yeah.
So one question on your GCDW explanation, you look discrete on one side and continuous on the other. Is it continuous on both and interpolated, or is it only interpolated on one side?
Oh, you're talking about these figures?
No, the schematic where you introduced G.
Oh, this one?
Yeah. It looks like it's interpolated on one side and not the other, or is it interpolated on both? It is interpolated on both.
Yeah. This interpolation is very subtle. Did I randomly sample? I don't know. This is just
You've done uniform sampling, but because the points are bunched up together.
Yes, actually, yeah. So the way that the alignment works is you define it at uniform points. In this case, on X, so on the pink one, and then it can align to wherever it wants on the orange one, and these two happen to align to a very similar spot, but there very much is an interpolation.
Does it have any mechanism to then undo the regular alignment initiation?
What do you mean?
For some reason, it's discovered that initial regular spacing among lines is a very coarse outline.
Oh, right. So we can differentiate through everything in DTW using this formulation. So in principle, you can differentiate with respect to the sampled interpolation times. But the problem about that is you have these nasty temporal ordering constraints, right? So I think people deal with this in like trajectory optimization as well, where you want to assume like piecewise spline interpolation between your sampled points, and then you can put this as a decision variable in your optimization, and the conclusion is, oh God, like it makes it like so much harder. And so I did look at this, and in principle we can do this, but we have not seen whether or not
if you want to look into that, you have to look at the difficulties around the time element operator.
Yes, right, yes. So this would be something interesting. So there's a lot more capability that GDDW affords. Like actually with GDDW, we can do like differentiable constraints as well, and differentiable regularization. Like everything is differentiable here, but we haven't really investigated that. We don't really know what to do with it yet, if I'm being honest. Thanks, Terry. Yeah, sure. Of course.
So if I understand correctly, I guess based on your process, when you don't convert, you don't
Yes. Correct. Yeah. Absolutely. Yeah.
And I guess the question is there a case, is it always better to do that, or is there a case for, on one hand, you have the older methods that provide
Right. Yeah. I mean, that's a good question. I mean, in our method, you can just turn down the threshold, and it will accept in practice. But in terms of the actual other methods, it could be. So maybe you can make multiple predictions, and then you can. So with these retrieval systems, sometimes what you might want to do is you might want to have multiple hypotheses, and then you can do a post-processing step where you do geometric verification. You can do spatial verification. Something a bit more expensive and spicy, but if you use it sparingly to good effect, it could quite be useful. So certainly some of the retrieval-based methods where you can retrieve multiple candidates and then re-rank them later would also be very, that would be a case where you maybe don't want to wait. You just give and then you check later. Yeah, ask for forgiveness later. Yeah. Oh, right. Well. Yeah. So what do we see here? Like when there's not too much aliasing, 10 to 20 meters or something, and things converge. Whereas at night it can be quite challenging, and sometimes you can be waiting like 50 to 100 meters for anything meaningful to happen. Yeah. So it can take quite a while. But at night, like everything's, at least using these image retrieval methods, everything's pretty cooked. So I don't think you can win. Driving, yeah. Yeah. Yeah.
I guess practical you do then in that meantime you would just run on the road.
Yeah, just try not to go off the road, yeah. just keep going, don't go off the road.
On the project two, I guess I'm interested in that optimized state that you introduced in there.
Yeah, sure.
Can you say a bit more about how that came out to be and sort of, is it like one state with the ability having multiple states?
Yep. Oh, right, yeah. Yeah, so one state turns out to be enough. So you can have multiple states, especially if you want your hidden Markov model to account for lag, for a delay, right? You might look at multiple time steps. But in this case, we found that putting in a single shortcut connection, so it's a single state. You might have like 10,000 places, but you have one extra state. And it's just a mechanism for the belief to be able to move very rapidly between different components of the state. So a lot of the belief, the mass, can actually transition to the off-map state, and if the measurements concur in a different area of the map, it can actually come straight back again. And the transitions are heavily informed by odometry. And part of that is computational. If you have a single extra state, I use a sparse matrix representation for the transition model, and adding in a single extra state doesn't actually add any overhead, at least in terms of the compute. So part of it is linear algebra, part of it is, it just happened to be enough for it to work.
So how does so it's an extra state in nature, and obviously this state is connected to all the others.
Yes, one densely connected state, correct.
So how do the condition probability behave in that story there?
Oh yeah. So basically, if there's a lot of mass in the off-map state, it uniformly disperses back. I didn't have time to do this when I actually submitted the paper, but you can easily inform the transitions based on the odometry, if that makes sense as well, the transitions back onto the map. But the transitions off the map, the transition probabilities are heavily modulated by odometry. So you see here, I'm expecting to turn right, but I'm not. And so that starts to shift the mass pretty aggressively into this new state. So that the states are mainly governed by odometry. I think even without odometry, it seems to still do something, but with odometry, it's obviously much better.
I guess you didn't go too much into some of the actual results that have quantification.
Oh, yeah. So that's a good question, because I evaluate on tasks that are different to other place recognition tasks. It's very difficult. So I did evaluate against comparable methods. So I guess one limitation of the second body of work is I compared against other filtering-based methods. And in the first approach, I compared to a much more broader range of methods. So we looked at different ways you can integrate sequence information with place recognition, like sequence matching, like stuff from SeqSlam, as well as stuff from Cyril Stuckness's group at the University of Freiburg? I always get it wrong, sorry. Anyways, they do like graph search approaches as well. And maybe both. So graph search approaches as well. So we compared against two different paradigms and we showed that our method does outperform those. In this one, it's certainly quite different. And in the last one as well, taking a nonlinear optimization approach, I guess the focus there is more from the machine learning perspective, showing that we can do these differentiable temporal alignments. So we didn't actually compare against other place rec methods because it wasn't designed to be a place rec paper. I think comparing this against other methods would be interesting for future work, but it wasn't the right decision for the actual paper that we submitted. So I don't have an answer. Sure. Oh, what do I think? Yes, I mean, like we did compare against other comparable methods which take image sequences. So I certainly think we do significantly outperform those. And I don't recall any new methods of integrating sequence information. I think a lot of new methods in the literature around learning new features, new image processing methods, rather than evaluating the actual algorithms to incorporate sequence information. So in terms of our methods being state-of-the-art, in terms of incorporating sequence information, I believe so. That's what I think, but I would need to think more about how I would evaluate that comprehensively in a watertight way. So I don't know, I think so, yeah. I'm happy to take more questions if that's not satisfying. I do. Yeah, sure. Oh, sure, yeah, I love talking about DTW. Oh, right. Right. So DTW is designed to handle changes in velocity because you're warping time, right? And so DTW is absolutely designed to handle nonlinear changes in velocity between query and reference, which is a beauty. You can think of DTW maybe as a generalization of SeqSlam, but you don't do linear sequence searches. You allow for the whole nonlinear sequence search. In terms of a different vehicle, I think the limitation is really in the data sets. So the way we evaluated on Oxford is, maybe I can show here. So this part of the map is used for training, and this part of the map is used for testing. And for testing, we actually evaluated on different dates as well. You see, so yeah, I think we did a fair evaluation on the test set, but validation and train are within this slice of the actual map. Yeah. Yeah, you could. No, not at the moment. I think it's a limitation of the data sets. I think if I had more time and more nighttime images to actually incorporate, then I can see probably performance improvement. But I think like fundamentally, this is just refining the network to do better for the sequence alignment task. I'm not sure if it automatically translates to generalization in terms of conditions. Yeah, that answers your question.
I had a question with your second project.
Yep.
And I guess at the end, you mentioned you'd be interested in looking at multi-session mapping and combining maps across different traverses. Do you think if you were to pursue that, would you go for like a unified embedding for particular places on your map, or do you think you would store multiple embeddings?
Oh yeah, so if you make data associate, so well, that's going to be the contribution, I suppose. I don't know yet. I have been thinking about this. So there are many different paradigms that you can use, like principled approaches or just hacks, to do like map sparsification as well. Like when do we combine nodes? When do we not combine nodes? There's the high dimensional computing stuff. Maybe you can just sum the embeddings and do like a normalized cosine distance for retrieval, for instance. Maybe that would work, maybe that wouldn't. And I think I would have to just code a lot to have a good answer to that question. Yes, but there are lots of details like map maintenance as well and sparsification and stuff. And these are the considerations that you would actually have to do when you actually build an actual system.
Thanks for the talk, being really great work. for second and first project, the measurement model that relates the images and the likelihood of the images. How did you derive those? How principled are they? And if you would do it again today, would you? How sensitive?
Oh yeah, I was hoping someone would actually ask that. So it's a simple transformation of similarities. So the thing is, this is like the measurement models are a fundamental generative process. Like in SLAM where you have a laser scanner, we know that if this is the actual distance to the actual landmark, and you see in probabilistic robotics, you have the multimodal distribution in terms of how the measurements might actually be generated. There's a lot of intuition here. Here, the measurement model, if you actually think about it in a more principled way, it's saying, we want to evaluate the likelihood of seeing this image given we're at this particular place. And there's some sort of, how do we describe the generative process? If we're at this place, what sort of descriptors will be generated? What sort of distribution is this? And I think if you want to do it in a principled way, for each place you would need many, many images, and you would need like a generative model at each place, and you need a generative model which can actually evaluate the likelihood. And when I went down that road, I went, oh, that's not a good idea. Like there are no data sets for this. This seems like not a good idea. And so we came up with a much more simple transformation, and part of the simple transformation is we don't need to change anything underlying for the methods, and it seems like even with something really stupidly simple like this, it still provides meaningful uncertainty quantification in cases where we actually need it. So would I do anything different? The answer is always yes, but I think doing it in a proper principled way, I don't really have a good solution as to how to do that at the moment, if that answers your question. Yeah, how do we generate images from a place? I mean, that's cool, I suppose, yeah.
Yeah, thanks for that talk. I have a question about DTW.
Sure, yeah.
And kind of the reference sets.
Oh, yeah, yeah.
How do you deal with the fact if the reference set causes and then there's multiple images of the same place at different times, or even if the car reverses and things like that?
Good question. So DTW is designed to handle nonlinear changes in velocity. So even if the car stays still, DTW in principle can handle that. If you apply too much regularization in the formulation that we have, the regularization kind of pushes it forward. So too much regularization might be bad. So maybe if we can detect that the images are standing still and modulate the regularization accordingly, that would be a great improvement to the model. In terms of going backwards, DTW typically has monotonicity constraints, but you can relax that. We've got this inequality constrained nonlinear program, and we go, oh, okay, well, let's just put this less than 0. You can do that, I suppose, and maybe that would be useful. So it's flexible to that, but we did not evaluate on that. We wanted to get it working first, and then we can probably relax it in future work. Yeah, you probably get nonsense, yeah, correct. That is my prior, but there's only one way to find out, I suppose, right? Toby?
Thank you. Quick question. What happens if your underlying image retrieval method gets better by 5%? How much will your equivalent technique benefit from that?
I think we kind of evaluated on blah, blah, blah. I mean, 5%, because it depends on the uncertainty, like what does 5% mean? But we evaluated on different image processing methods. So DV is dense VLAD. Dense VLAD is actually very much stronger than net VLAD, despite no learning involved. And typically we see that, convergence, let's say for nighttime, convergence is certainly quicker. In terms of the results are certainly much better as well. We're changing to a stronger image retrieval approach, and it certainly does work better on average. Yeah.
So the cool things about your first second project are that you can combine autonomy measurements and do all this probabilistic filtering and smoothing back and forth. How would you combine that back into project 3 and also handle going off the map?
Oh, yeah. Well, I guess like the multi-session mapping problem I was actually thinking of, I've been developing that a little bit in C++, which has made it much longer than it should have taken. But anyways, that detail aside, you can actually add this off-map state into the nonlinear optimization. Yes, exactly. So you can take DTW and you can add this state as well, and you can inform the transitions using odometry and not. I have code around. You can do it. It doesn't work very well at the moment. I think filtering has this natural robustness to it, which I haven't been able to reproduce using nonlinear optimization. But I think including odometry and the softmap state is certainly possible with DTW, and I have made some progress around that. Yeah.
Okay, we run out of time for the first part of the proceedings, so thanks, Ming.
Okay, thank you.